Flying saucers. The mysterious discs that have fascinated people for decades. Reports describe objects moving across the sky in ways that seem to defy everything we know about physics, hovering silently, darting from one point to another almost instantaneously, and performing impossible turns that would crush anyone inside. Millions of sightings have been reported, and countless stories have been told, yet hard evidence remains elusive. When we look at these claims through the lens of physics, we begin to see why flying saucers, as popularly imagined, are so unlikely to exist. Richard Feynman, one of the greatest physicists of the 20th century, had a simple principle. What you cannot create, you do not understand. If humans cannot build a craft that performs these maneuvers, the laws of physics themselves may be revealing the truth. To understand why, we need to break down the problem step by step, using the science we know, analogies we can relate to, and thought experiments to illustrate the limits of what is possible. The first major obstacle is energy. Every movement in the universe requires energy, and the faster or more abruptly an object moves, the more energy it consumes. Many UFO reports describe objects accelerating to incredible speeds almost instantaneously. To imagine what this means, picture yourself in a car. If your car could go from 0 to 60 miles per hour in a fraction of a second, the force would throw you violently into your seat. Humans can withstand a few times the force of gravity for brief moments, but many reported maneuvers would produce forces hundreds of times greater. Any human inside would be instantly crushed. Even ignoring human vulnerability, the energy required to perform such maneuvers would be staggering. It is difficult to overstate just how extreme this is. Moving an object the size of a small car in such a way would demand an almost unimaginable energy source, one far beyond our current understanding or technology. Next, there is the problem of aerodynamics. Air does not simply vanish when something moves through it. Objects experience drag, turbulence, and resistance. Flying requires generating lift, whether through wings, rotors, or another propulsion mechanism. Most flying saucer designs, simple discs with smooth edges, are poorly suited for this. Flat discs generate very little lift and are aerodynamically unstable. If you try to throw a frisbee straight up and have it hover midair, it fails almost immediately. Now scale that up to a craft thousands of times heavier. The air would resist, turbulence would destabilize the object, and extreme heat would build up at high speeds. Even in the absence of energy limitations, aerodynamics alone makes the classic flying saucer shape highly impractical. The physics simply does not cooperate with the imagination. Gravity adds yet another layer of complexity. On Earth, every object experiences a constant downward pull. To hover, a craft must generate a force equal to its weight. To accelerate upward or sideways, it must generate even more force. Many UFO reports describe instant vertical movements, rapid horizontal shifts, and sudden stops. For any object with mass, achieving such movements would require generating forces far beyond what any known material engine or energy source could sustain. It is not just a matter of moving through space, it is about counteracting the fundamental pull of gravity, which cannot be ignored. Finally, Newton's laws of motion introduced the concept of inertia. Objects resist changes in motion. Turning, stopping, or accelerating abruptly at high speeds creates enormous internal forces. A sudden sideways turn at hundreds or thousands of miles per hour would be catastrophic. Structures would tear apart, materials would fail, and any occupants would be crushed long before the maneuver completed. Even ignoring human fragility, these physical stresses are extreme and unavoidable. When we consider energy, aerodynamics, gravity, and inertia together, it becomes clear that flying saucers, as popularly described, face multiple, insurmountable barriers according to known physics. The reports that capture our imagination often conflict with the rules that govern the universe. Yet understanding these limits is not discouraging. It provides clarity. It teaches us to differentiate between phenomena that could be possible and those that challenge the fundamental laws of reality. It reminds us that physics, while sometimes counterintuitive, is a reliable tool for understanding what is actually achievable in the cosmos. Even if we could somehow generate enough energy to overcome the incredible forces of acceleration, there is another obstacle that is just as unforgiving: the behavior of air itself. Air is not empty space. It is a fluid that pushes back against anything moving through it. Every airplane, helicopter, or drone must contend with this invisible but relentless resistance. Engineers spend decades designing wings, propellers, and fuselages to manage airflow efficiently. The classic flying saucer design, a flat, smooth disc, simply does not cooperate with the air. It is aerodynamically unstable. Without carefully designed lift surfaces, it cannot hover, accelerate, or maneuver without tearing itself apart or generating extreme turbulence. Imagine throwing a paper airplane. With the right angle and a gentle flick, it glides gracefully across the room. Now imagine throwing the same paper plane straight up and expecting it to hover midair. Air immediately resists the motion, pushing against the flat surface, destabilizing it and causing it to tumble. Scale this thought experiment up to a disc-shaped craft weighing several tons, and the problem grows exponentially. The forces of air pressure, drag, and turbulence would be enormous, and the structural integrity of the craft would be severely tested. At high speeds, the air itself becomes a destructive force, generating friction and heat that can melt or destabilize materials. A disc-shaped craft attempting rapid maneuvers would have to overcome all of these effects instantaneously, an impossible task with any known technology. Lift is another subtle but crucial problem. Helicopters, airplanes, and birds generate lift by redirecting air downward. Wings and rotors are shaped specifically to create a pressure difference, allowing the craft to stay aloft. A perfectly flat disc, however, does not create lift efficiently. To hover, it would need to push an enormous amount of air straight downward with incredible precision. Any imbalance would result in instability, spinning, or even flipping the craft entirely. The reports of flying saucers performing precise, silent hovering in calm air contradict everything we know about fluid dynamics. The universe, as Feynman might remind us, is consistent. Air behaves the same way for a disk as it does for a frisbee, and there is no secret loophole that allows a craft to ignore these fundamental principles. Even if we entertain the idea of advanced propulsion systems that somehow generate lift without wings or rotors, the craft still faces the problem of inertia. Newton's first law states that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. Rapid acceleration or sudden directional changes generate forces proportional to mass. A heavy disk attempting an instantaneous 90-degree turn would experience forces thousands of times greater than gravity. Any internal components or hypothetical occupants would be destroyed. The energy required to counteract these forces is not just high, it approaches levels that are physically implausible given the size, mass, and density of a craft reported in UFO sightings. The interplay between air resistance, lift, and inertia creates a chain reaction of challenges. Even ignoring gravity, even assuming near perfect energy efficiency, even if we could invent materials strong enough to survive impossible forces, the craft would still have to manage air in real time. Every instant of motion creates turbulence, which interacts with the craft's shape, generating unpredictable feedback that destabilizes it. The physics of fluids is unforgiving. It does not bend to imagination or folklore. Observations of actual aircraft, birds, and even insects confirm this. Motion in a fluid is constrained by unbreakable laws. These considerations show that the aerodynamic and motion problems alone place severe limits on what flying saucers could do. The sudden shifts, rapid accelerations, and effortless hovering described in reports are inconsistent with the principles that govern the world around us. It is not a matter of skepticism or disbelief. It is the logical consequence of energy, air, and motion interacting in predictable, measurable ways. Understanding these limits does not diminish curiosity, rather, it deepens it. By studying what is impossible, we gain insight into what is possible, and we sharpen our understanding of the universe in ways that no story or speculation ever could. Gravity is relentless. Every object on Earth experiences a constant pull toward the planet's center. It is invisible, yet impossible to ignore. Every time a flying saucer is reported hovering, ascending, or performing sudden maneuvers, it must somehow counteract this downward pull. On the surface, hovering seems simple, just stay in the air. But the physics tells a different story. To remain aloft, a craft must generate a force equal to its weight. To accelerate upward, it must generate even more. The heavier the craft, the greater the force required. For an object the size of a small car, hovering alone demands an immense amount of energy, and accelerating in any direction multiplies that demand exponentially. Imagine holding a rock in your hand. Slowly lifting it off the ground is easy. It requires only a modest effort. Now imagine trying to throw that same rock 100 meters straight up in an instant. The force needed would be enormous. Your muscles would be incapable of generating it, and any object with the mass of a real flying saucer would require an energy source far beyond what we know how to harness. Every report of a disc-shaped craft performing rapid vertical or horizontal movements faces this same fundamental limitation. The laws of physics are unforgiving, and gravity does not yield to imagination. Inertia complicates matters even further. Newton's first law tells us that an object resists changes in motion. If a saucer is moving at hundreds or thousands of miles per hour and suddenly attempts to change direction, every part of that craft, its frame, its interior, and anyone inside experiences a tremendous force. The faster the motion and the sharper the turn, the greater the force. At the extreme speeds described in UFO sightings, these forces would be catastrophic. Any human or fragile material inside the craft would be crushed instantly, and even the strongest known materials would likely fail under the stress. The challenge is not just generating motion, but controlling it in a way that is survivable. Consider a thought experiment. A bicycle wheel spins easily when you turn it with your fingers. The forces are small and manageable. Now scale that wheel to the size of a building and attempt to spin it the same way in an instant. The forces involved are no longer trivial, they become destructive. The same principle applies to a flying saucer attempting sudden accelerations or sharp turns at extreme speeds. Mass resists motion, and any attempt to overcome that resistance is met with forces proportional to the mass and acceleration. The numbers involved are staggering, often beyond the limits of known materials and energy sources. Gravity and inertia work together to enforce these limits. Hovering requires counteracting gravity. Accelerating requires overcoming inertia, and turning at high speeds multiplies the forces exponentially. Every report of a flying saucer moving with impossible agility and sudden stops runs into the same insurmountable barriers. These are not minor technical problems. They are fundamental consequences of the universe's laws. Even the most advanced propulsion systems we can imagine would struggle to overcome these combined effects. Yet, in studying these limitations, there is insight. Understanding why flying saucers are physically impossible, as popularly described, sharpens our sense of reality. It teaches us to distinguish between observation and imagination, between the possible and the fantastical. Physics does not quash curiosity, it channels it, providing structure to wonder. The very constraints imposed by gravity and inertia reveal the scale and power of forces at play in our universe, reminding us that even what seems ordinary, the pull of Earth, the resistance of mass, is profoundly significant. In recognizing these boundaries, we gain a deeper appreciation for the delicate balance that makes flight possible at all, and for the precision required to navigate even our familiar skies. Even as we examine energy, aerodynamics, gravity, and inertia, we must admit there is a fundamental principle that Feynman loved to emphasize. The universe contains things we do not yet understand. Physics is not static. It is a constantly evolving map of reality, refined and corrected as we explore deeper layers of nature. Perhaps there are mechanisms for propulsion force or energy that humans have not yet discovered. Maybe the universe has loopholes we cannot currently exploit, or physical phenomena that appear impossible from our limited perspective. But it is important to recognize the distinction between the known laws of physics and pure speculation. Until we have evidence, the reports of flying saucers performing impossible maneuvers remain inconsistent with everything we do know. Human perception adds another layer of complexity. Our brains are wired to recognize patterns and assign meaning, even when the evidence is incomplete. A light moving across the sky, the reflection of a plane's landing lights, or even natural phenomena like meteors or atmospheric electricity can be interpreted as something extraordinary. Stories and cultural expectations shape what we report. The classic disc-shaped craft, glowing or hovering silently, is as much a product of imagination and storytelling as it is of observation. This does not make the experiences any less real to those who witness them, but it does complicate the question of physical reality. We see what we expect to see, and our minds fill in the gaps with patterns that fit our beliefs or cultural narratives. Cognitive biases, combined with the limits of human observation, make it difficult to separate reality from perception. Observers may misjudge distance, speed, or size. Lights can appear to move erratically due to perspective shifts or atmospheric distortion. These factors, when combined with the powerful appeal of mystery, can produce reports of objects that seem to defy physics. Feynman would likely argue that before concluding the impossible, we must rigorously explore all explanations grounded in known science. Extraordinary claims require extraordinary evidence, and in the absence of such evidence, physics remains our most reliable guide. Yet there is value in contemplating the impossible. Human curiosity drives inquiry precisely because we encounter limits. Flying saucers may not exist as imagined, but the act of questioning why they cannot exist illuminates deeper truths about energy, motion, and the structure of the universe. It forces us to think critically about cause and effect, to analyze assumptions, and to apply principles consistently. The study of impossibility is itself a profound form of learning, revealing the elegance and rigor of the laws that govern our reality. Every time we investigate why a phenomenon is impossible, we refine our understanding of the natural world and expand the boundaries of human knowledge. This intersection of physics and perception also invites philosophical reflection. The universe is consistent, but our interpretations of it are not. Human imagination is both a gift and a challenge. It allows us to conceive of worlds beyond our experience, yet it can lead us to conflate fantasy with reality. Recognizing the limits of our knowledge, while rigorously applying the laws we do understand, cultivates a mindset that is simultaneously humble and inquisitive. We learn to marvel at what is real, while appreciating the ways our minds shape the stories we tell about the unknown. In this way, even impossible ideas like flying saucers become tools for thinking more deeply about the universe, prompting questions that stretch our understanding without ever betraying scientific rigor. So what does all of this teach us about reality, the universe, and the way we perceive it? Flying saucers, as they are popularly described, may be physically impossible, but this conclusion is not a defeat for imagination. It is an invitation to think more clearly and more deeply about the world around us. Physics sets limits, yes, but those limits are not constraints on wonder. They are guides that show us what is possible, what is plausible, and what stretches beyond the bounds of known science. Understanding these limits does not diminish curiosity, it refines it. It teaches us to ask better questions, to approach the unknown with both humility and rigor, and to appreciate the elegance of the universe as it actually is. The universe is vast and complex, governed by laws that are consistent and measurable. Energy cannot appear from nowhere. Mass resists acceleration. Air pushes back when objects move through it. Gravity is an invisible force that cannot be ignored. These principles are not arbitrary. They are the structure on which everything else rests. Yet they do not stifle imagination, they empower it. Knowing the boundaries of what is physically possible allows us to explore more deeply the questions that matter. We can dream of advanced propulsion, of technologies that bend our current understanding, but we do so with awareness of what would be required to make those dreams real. Imagination guided by science becomes a tool for discovery rather than a source of delusion. Human perception and storytelling complicate our view of reality, but they also reveal something profound about our minds. We see patterns where none exist, we interpret ambiguous stimuli through cultural lenses, and we create narratives to explain the unexplainable. This is not a flaw, it is a remarkable feature of our species. The very fact that millions of people report similar shapes and behaviors in the sky speaks to the universality of human cognition, our innate drive to seek meaning, and our desire to confront the unknown. Physics and psychology together help us disentangle reality from perception, allowing us to appreciate both the world as it is and the imagination it inspires. There is also a subtle beauty in confronting impossibility. Flying saucers may defy the laws of physics, but studying why they cannot exist teaches us far more than simply dismissing them. It sharpens our understanding of energy, motion, and the forces that shape our universe. It reminds us that the ordinary, the way a rock falls, the way air resists, the way inertia operates, is extraordinary when we pause to measure it carefully. Everyday phenomena that we take for granted are, in fact, governed by precise, inspiring principles. Learning the universe's rules transforms the ordinary into something magical, even when the impossible remains out of reach. Ultimately, science invites a form of wonder that is disciplined yet profound. It asks us to marvel at the cosmos while adhering to evidence, to explore with curiosity but without deception. Recognizing the impossibility of flying saucers does not shrink our sense of mystery, it clarifies it. It encourages us to see reality not as a collection of myths, but as a coherent, astonishingly intricate system, full of patterns, surprises, and discoveries waiting to be made. Understanding the constraints of physics changes the way we see the universe. It makes the impossible vivid, the improbable compelling, and the real profoundly beautiful. The next time you look up at the night sky, remember that the universe operates on rules far stranger and more precise than any story of disks darting through the air. In the silence between stars, physics speaks with clarity, and it invites us to listen, not with blind belief, but with a mind open, curious, and alive. As we reflect on what physics tells us about flying saucers, it is worth stepping back and considering what this means for the human experience of reality itself. The universe does not conform to our desires, our stories, or our imaginations. It follows principles that are precise, measurable, and consistent. Yet within these constraints lies freedom, the freedom to explore, to understand, and to marvel at the intricacy of the cosmos. Flying saucers, improbable though they may be, serve as a lens through which we can examine the very nature of knowledge. They remind us that reality is not dictated by wishful thinking or anecdotal reports. It is dictated by the interplay of energy, motion, and matter. Every law of physics, from Newton's laws of motion to the principles of thermodynamics, is a rule that governs the possible. These rules are not limitations imposed by a higher authority. They are descriptions of how the universe actually behaves. They tell us why an object cannot accelerate instantaneously, why a disk cannot hover silently without generating enormous turbulence, and why any occupant would be subjected to forces beyond human survival. Understanding these boundaries is not a matter of skepticism. It is a celebration of the universe's internal logic. When we learn why something is impossible, we also learn why everything else works the way it does. There is an elegance in these constraints, a beauty in the way the cosmos balances forces, energy, and motion to maintain coherence. Yet the human mind continues to imagine what lies beyond these boundaries. We tell stories, construct myths, and report sightings of phenomena that challenge our understanding. This tendency is not a flaw. It is a vital part of human cognition. It is the spark that drives curiosity, fuels inquiry, and inspires scientific discovery. By confronting the impossible, whether it be flying saucers or faster than light travel, we refine our questions and deepen our understanding. Physics does not stifle imagination, it channels it. We learn to separate plausible possibilities from fanciful ideas, to distinguish between what can be realized and what serves as a metaphor for wonder. There is a profound lesson in this interplay between imagination and physical law. The universe is not only stranger than we imagine, it is stranger than we can imagine. Yet it is also accessible. By observing carefully, thinking rigorously, and questioning consistently, we can uncover truths about reality that are astonishing in their precision and scope. Flying saucers, whether real or imagined, act as a mirror. They reflect not only the mysteries of the sky, but the patterns of our minds, the ways we perceive, interpret, and sometimes embellish what we see. Understanding why these crafts are physically impossible illuminates both the cosmos and ourselves. Finally, contemplating impossibility encourages humility. We are creatures bound by our senses, our brains, and the instruments we build to extend them. The universe does not bend to belief, it bends according to law. This realization transforms our curiosity from passive wonder into active investigations. It teaches us to celebrate the limits of knowledge as much as the discoveries themselves. Reality is not less magical because it is governed by rules. It is more profound. The stars, the planets, the forces we feel but cannot see, all of it operates in ways that are beautiful, awe-inspiring, and sometimes, at first glance, counterintuitive. Accepting these truths reshapes the way we live, the way we explore, and the way we imagine. Science does not kill mystery, it elevates it. And in understanding why flying saucers cannot exist, we glimpse the deeper, more wondrous patterns that govern the universe, and we are invited to think, question, and marvel in ways that are profoundly human. Exploring the impossibility of flying saucers does more than address a single phenomenon. It opens a window into how we engage with the universe as a whole. Physics, at its core, is a language describing patterns, relationships, and consistent behaviors that govern matter and energy. Every law we uncover is a map, a framework that helps us predict what will happen if we act in a particular way. It is tempting to wish that the universe would accommodate our imaginations, to hope that objects could defy inertia, gravity, or energy constraints. Yet the universe remains indifferent to desire. It operates according to principles that are impartial, consistent, and extraordinarily intricate. This impartiality is not a limitation. It is the source of the universe's profound elegance. Every star, every planet, every particle follows the same rules, and by understanding those rules, we gain a clarity that is almost spiritual in its beauty. Human beings are storytellers. We take what we see, often fleeting glimpses of lights, clouds, or reflections, and weave narratives that fit our cultural and personal expectations. Flying saucers are as much a story about humanity as they are about the sky. They reflect our curiosity, our fears, our desire for the unknown, and our wish to glimpse something beyond ordinary life. Cognitive biases shape how we perceive the world. The mind fills gaps, interprets movement, and seeks patterns even where randomness exists. Understanding this helps us appreciate why extraordinary claims arise and why they capture our imagination. Physics and psychology together form a lens for seeing both the universe and ourselves with greater accuracy, highlighting the intersection between external reality and internal perception. There is a subtle lesson in acknowledging impossibility. It teaches patience, rigor, and humility. To ask why something cannot exist requires careful thought, disciplined reasoning, and attention to detail. In the process, we sharpen our capacity to see connections, measure forces, and understand the mechanics of the universe. The impossibility of flying saucers does not stifle wonder. It enhances it. When we confront what cannot happen, we simultaneously illuminate what can. A hummingbird's wings, the flight of an eagle, or a rocket's launch are remarkable precisely because they operate within physical constraints. Each successful instance of flight is a triumph over resistance, inertia, and gravity, an achievement that is both predictable and extraordinary. This perspective also reshapes our approach to scientific exploration. We learn to value evidence, to question assumptions, and to test hypotheses rigorously. Imagination becomes a tool for inquiry rather than a source of error. By studying the limits of what is possible, we cultivate the skill to innovate within those limits. Human progress has always been driven by understanding the rules before bending or expanding them. The process of examining impossibility strengthens our intuition, guiding us to ask the right questions, design better experiments, and develop technologies that push boundaries without violating reality. Ultimately, the lesson extends beyond flying saucers or energy calculations. It is a lesson about curiosity itself. Wonder is not the suspension of disbelief. It is the disciplined engagement with reality, informed by observation, reason, and creativity. The universe is vast, complex, and often counterintuitive, yet it can be explored, measured, and understood. Physics provides a compass, guiding us through phenomena that challenge perception and intuition. In confronting impossibility, we glimpse the elegance of the cosmos, the precision of its laws, and the ingenuity required to navigate it. We learn to appreciate not just the things that exist, but the structure that makes existence coherent. The act of asking why something cannot happen transforms curiosity into insight, fear into understanding, and imagination into a deeper appreciation of reality. By recognizing the impossible, we discover the extraordinary beauty of what is possible, and in that recognition, we begin to see the universe and our place within it in a profoundly new light.